Physics students, this is Dr. Brenzy here, and this is lesson 10.1, and this is going to be first lesson on thermodynamics. And in this lesson, we're going to be able to describe the relationship between temperature and molecular kinetic energy in an ideal gas. So let's go ahead and get started. Okay, so the essential question that we're trying to answer today is, what is temperature? We know it has something to do with how hot or how cold something is, but what's really going on in the physical world? What are we actually measuring physically when we measure temperature? Now, this is going to actually be, it could be a hard question to answer, or I could give it to you right away, but I'm going to actually go through the process of proving to you what exactly temperature is, and that's going to take a while. As a matter of fact, it's going to take all of this video and maybe even a little bit of the next video, but I want you to have a thorough understanding of what temperature is. So I can't do that unless I actually go through and go through this process of proving it to you. So let's start off by considering an ideal gas. So an ideal gas, there are three key properties to it. First of all of the collisions that happen in an ideal gas are elastic, which means energy is conserved, kinetic energy. We don't have any attraction between the gas molecules in the wall or the gas molecules and each other gas molecule. So there's no attraction between the gas molecule and anything. It also obeys the ideal gas law. And this might not be the form of ideal gas law that you're used to seeing in chemistry class, but let me explain it to you. So we have P. Let's see if my pointer will come up here. The answer is no. But anyway, we have P stands for the pressure of the gas. V stands for the volume that gas is contained in. So we have P times V. And then on the other side, this is the part that you might not be used to, capital N stands for the total number of molecules in the gas. In chemistry class, you're used to thinking about the number of moles, and that's a small letter N. But in physics, we like to think of the number of molecules. K is what's called the Boltzmann constant, and that Boltzmann constant is given to you on the right-hand side there. That's 1.38 times 10 to the negative 23rd joules per K, and K stands for Kelvin. Kelvin is actually the temperature scale that we use in the ideal gas law. The significance of that temperature scale is that when the temperature is zero, then we are at what's called absolute zero, which means there is no movement of molecules inside that gas. There's no energy. So that's the ideal gas law, and we're going to use that ideal gas law to actually prove what exactly does temperature measure. All right, so let me go ahead and advance my slide here. Let's see what. All right. Okay, now let's continue with a little observation here. I have to actually. Oops. Hold on here. Hold on a moment. I want to pull up a little demonstration here for you. So let me. Okay. Let me reset this guy. Okay, so this is a little simulation of a gas. And what we can do is we can push down on this handle like this, and we can introduce gas molecules. And nothing's happening. I don't know why. My computer's going really slow. Let's try it again. Let's try 1. It is doing nothing. Oh no. Oh, that's because I gotta play. There we go. All right, now we gotta give these gas molecules a little time to settle in. All right. Okay, I think they've settled in long enough. So what you may notice is that the motion of these gas molecules is like very random. Now, what would happen to this gas if, say, we were to remove some heat? So let's remove some heat. And come on. cold. There we go. All right, so I'm putting some ice on this thing. Actually, not ice, but I'm taking heat out of the system, which actually lowers the temperature. You'll see the temperature on the top right. And what you may notice is that the gas molecules are going slower and slower. They're going super slow. So this might represent a gas that is at 10 Kelvin. If you can see that little diagram up there, that little thermometer. You'll notice the gas molecules are moving really slow. The other thing you might notice is that there are very few collisions with the walls. They're not happening, the collisions with the walls are not happening very fast. So if I were to look up in that upper left-hand corner, there's a collision, there's another one, tick, 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 tick. Okay, so up in that upper left-hand corner, there aren't very many collisions that are happening very often. But what happens if I add some heat to this and raise the temperature? So let's go ahead and do that. Let's raise the temperature. Let's get this gas hot again. So I start raising up this temperature. All right, temperature's coming up. And you'll notice that the gas molecules are actually moving faster. All right, and this might be representative of a gas that is slightly warmer than room temperature. Actually, it's quite a bit warmer than room temperature, so let's lower that a little bit. Get it back to about 300 Kelvin, which is about room temperature. Oops, I'm going the wrong way. 300. Close enough. Okay, now if we take a look at that very top left-hand corner of the box, and we're going to kind of like time the collisions here. Here we go. Tick, 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 tick. You can actually hear the rate of those collisions actually increases quite a bit from when we had it at a low temperature. Okay, well. So, what are some observations, key observations that have we made here about this gas? Well, first of all, when we raise the temperature of the gas, we observe that there are more collisions between the gas molecules in the wall. And those collisions cause the gas to exert pressure on the walls. That's the source of a gas's pressure acting on the walls. So could this phenomenon give us some insight into what temperature measures physically? That's what we're going to answer. So we're going to use that idea of pressure and how fast these molecules move to derive some sort of definition of temperature. All right, so let's consider a very small section of a wall on that box. In order to make life simple, or simpler for us, visually and mathematically, let's make some assumptions. So first of all, let's assume that the molecules can only travel along the x direction. So they can either go left or they can go right. Now we'd expect, since each molecule's direction is completely random, we'd expect half of these to be moving to the right. It's not cooperating with me. Hold on here. I had a little graphic here. All right, there we go. There's the graphic. So half of these molecules are moving toward the right, and the other half of these molecules are moving toward the left. And all of them, we're going to assume, have a speed equal to Vx. So let's make those assumptions and see what sort of insight we can get into temperature. All right. So let's ask ourselves, how many collisions happen with this little section of wall here? It's given to you as a little disc. So imagine a circle, a small circle on the wall of that cylinder. How many collisions will happen on that little section of wall in an infinitesimal time dt? Now what we can do is we can think of a cylinder projected away from that piece of wall, and only molecules inside that cylinder will make it to the wall in time before this little infinitesimal time dt elapses. So, for example,
I have a molecule that's inside, like this guy. This guy will be able to hit the wall in time, but this guy out here, I have another one right there, that will not be able to hit the wall in time. And if I actually draw the velocity vectors of these two, oops, wait a minute, what happened to my velocity vectors? I'll explain that in a minute, but let me go to the velocity vectors. There we go. So this one will be able to hit the wall in time, but this one out here, on the other hand, will not be able to reach the wall in time. Well, what is the length of this cylinder? Well, it happens to be its velocity, the velocity of the molecule, which is Vx, times our infinitesimal time. That is how far this molecule will go in a time dt. So if it has a section A, it will have a length Vx times dt. Now, how many molecules are inside this cylinder? Well, if I want to compute that, all I have to do is figure out the density of the gas, which is the number of molecules inside the box divided by the volume of the box. And then I just have to multiply that times the volume of this little cylinder. Well, the volume of this cylinder is its area times its length here. So I can replace V cylinder with area times this. And now I have an expression for how many molecules are inside this cylinder. These are the only molecules that will have the capability of hitting the wall in our little infinitesimal time dt. Now, that's not the number of collisions that happen with the wall, because if we ask ourselves how many collisions happen with the wall in that infinitesimal time, we got to remember that only half of these molecules will actually be moving toward the wall. So what we have to do, and there's a little graphic that shows you, oh yeah, half of them are moving toward, half of them are moving away. We made that assumption earlier. So the number of collisions that happens is just half the number of molecules inside the cylinder. So now I have to multiply this times 1/2. Okay, so this is the number of molecules inside the cylinder right here. And then we multiply it times 1/2 to get the number of collisions. So that's how many collisions will happen with this wall in an infinitesimal time dt. Where are we going with this? Why do we want to know the number of collisions? Well, because the number of collisions might give us an idea of how much pressure is exerted on this wall. Ignore this little guy down here for now. Ignore that for now. That'll pop up. Actually, that's just a little error on my part. But now let's ask ourselves, how much force does each collision exert on the wall? So we figured out how many collisions happen in that cylinder, but how much force does each of those collisions apply to the wall? Well, in order to do that, let's think about momentum. An ideal gas will only have elastic collisions with the wall, so kinetic energy and momentum both have to be conserved. Now, it's really the fact that these are elastic collisions that might give me some insight into what's happening here, because the wall, first of all, the wall doesn't move, which means the molecule must have the same speed before and after the collision in order to conserve kinetic energy in the system. So if you can imagine this, so we could draw a before and after picture. Our before picture is a molecule moving toward the wall, and its total momentum is positive m times Vx. Now the wall doesn't move after the collision, so its velocity is still 0, so it carries no momentum, or approximately 0 momentum, actually. There is actually a very small amount of momentum, but we're going to essentially say that it's 0. Now, in order for kinetic energy to be conserved, the molecule has to be moving with the same speed so that it has the same amount of kinetic energy, but now it's just going to be moving in the opposite direction. So now its momentum is negative m times Vx. Well, that means that our change in momentum
in a collision is -2 times m times Vx. You take the final momentum minus the initial momentum. Okay, I wasn't asking about change of momentum though. I was asking about how much force does each collision exert on the wall. Why would I need to figure out what the change of momentum is? Well, if you think back to Unit 4, we can use the momentum impulse theorem to make a connection between the change of momentum and force. The momentum impulse theorem states that the change of momentum has to equal the impulse, and the impulse that this molecule exerts on the wall is the force it exerts times this infinitesimal time dt. So here we have substituted our change of momentum here, and we set that equal to f dt. And now we have an expression for how much force each molecule exerts on the wall. -2 mvx over dt. Okay, so I know how much force each molecule exerts on the wall. I know how many collisions occur on the wall in a time dt. So I think I can figure out the total amount of force that the entire gas inside that little cylinder exerts on the wall if I just multiply those two things together. And then that will give me pressure. So what pressure does the gas exert on the wall? Well, that is total force per unit area. That total force is the force caused by each collision times the number of collisions. We figured out both of these numbers, or an expression for them. The pressure is the magnitude of that force times the number of collisions divided by the area of the wall that we're interested in. So if I replace the magnitude of F with this thing right here, actually it's 2mvx over dt. That's what we came up with on the last slide. This is the number of collisions over here, 1/2 n over v times this quantity here. So that's the number of collisions. And then we divide that by A because pressure is total force divided by area. And if we do some math, and I clicked my button early, but if we do some math and looks like some things cancel out, then you will get n over v times m vx squared. And that is the total pressure that the gas exerts on the wall. So we figured out how much pressure the gas exerts on the wall. Well, why in the world is that useful? Why did I want to know the total pressure? Because what I can do now is I can plug this back into the ideal gas law. So let's go ahead and do that. Let's bring the ideal gas law back into the picture. So the ideal gas law, here it is again, PV equals N times K times T. Now let's replace pressure with that quantity we just came up with in the last slide. Now we can do a little algebraic manipulation. We can cancel out some n's and some v's, and we get this expression right here. mvx squared equals k times t. Well, that left-hand side looks awful familiar to me. That looks very, very familiar. Because if I multiply that times 1/2, what I have is the kinetic energy of an individual gas molecule. So that means the kinetic energy of an individual gas molecule is 1/2 times K times T. Now we have a physical representation of what temperature is. It's not just how much cold or how hot something is, which are kind of like touchy-feeling things. We actually show that for an ideal gas, temperature is a measure of how much kinetic energy is in each molecule. Now, that's not quite true, because we've made a couple of assumptions that don't really occur in actual gases. But I'm going to address that next. But I want to split this video into two parts so that this one isn't overly long. So go ahead and go on to the second video, and we'll actually talk about those two assumptions and how we can handle those, and get a better idea of what goes on in an actual ideal gas. All right, ladies and gents, I will see you shortly in the next video. Take care. Bye. Oh, you're kidding me. You're kidding me? Oh, no. Are you serious? Did I really not record anything? Did I really not record a thing? That thing was beeping all the time. When did it? Ah. Dang it. Oh, here we go.